being recorded as well.
Mm-hmm. So should we go ahead and start then, Tom? You want to introduce anything there, or want me to?
We just opened up the webinar. People are now joining. We will give them a minute to get set up with their audio, and then we can start.
Okay. Somehow my camera's not working there. Right. There we go.
Okay, at this point, you guys can begin whenever you're ready.
Okay. Well, good afternoon, everyone, or good morning, depending on where you may be located in the world here. My name is James Rickles. I'm the PI of the NHERI Lehigh experimental facility, and today we're going to host our annual virtual researchers workshop. The purpose of this is to illustrate our capabilities, project examples, and then guidelines for proposals. So that's our title here. What I want to state is that our other objective, or main objective really, is to acquaint the audience with the capabilities and resources that we have, and thereby the opportunity that you have to conduct research at our facility. And what we hope that comes out of this is that as researchers, you will write and submit proposals, research proposals, to the National Science Foundation that utilize our site. We're an open access site. As I mentioned, today's a virtual workshop. As you know, we have 2 workshops per year. The second one is an in-person workshop. It's to be scheduled for the 3rd week in November of this year. So, stay in touch in terms of visiting our website, and there'll be an announcement that will be posted. So with that, I'm going to hand this over to Dr. Joseph Saunders, who's our operations manager, and he'll go through some other objectives in our agenda.
Hi, everyone. Yes, so I'm Dr. Joe Saunders here. I'm just going to briefly walk through our workshop objectives and agenda, introduce the team here, and then hand it back over to Jim. So next slide, please. Yeah, so just a brief introduction to the team here. So Dr. Rickles, his PI, already introduced himself as the NHERI Lehigh EF team. Dr. Richard Sauce also here, co-PI. I am Dr. Joe Saunders, the operations manager. We have Dr. Leon Cow here. He's a research scientist here as part of the NHERI Lehigh team. We have Tommy Morello, our IT systems manager. Dr. Alia Amr, a postdoc research scientist, and then Derek Richmond and Sandy Nemeth, Atlas Lab manager and Atlas financial manager, respectively. So this encompasses the NHERI Lehigh team, and you'll hear from a number of us today. Can you go to the next slide, please? So our workshop objectives here. So our plan here is to, as Jim had mentioned, disseminate information regarding the NHERI Lehigh experimental facility, right? What we do, this sort of research that we do, and really focused on mitigating the effects of natural hazards on civil infrastructure. We'd like to communicate, right, our capabilities and what we can do. Can you hit the next bullet here? Yeah. So also, a focus here is to showcase our expanded capabilities that we've recently partook in. We've expanded our capabilities at the facility, including the real-time cyber physical structural systems testing facility. It's quite a mouthful, but increasing capability is something that we're always looking to do and expand our research capabilities. So we'll go into a little bit about some of the experiments that we've done in this facility using this new equipment, and showcase and highlight the research that we're currently working on in natural hazards mitigation. And then finally, we'll wrap it up with identifying and showcasing or showing how you can work with us and utilize the facility here, the experimental facility here. Next slide, please. So our agenda, so Jim with the welcome, myself with the brief overview. I'll hand it over to Jim with the science plan and overview of the facility, and then our experimental facility protocols and resources. Then Dr. Cao and Dr. Amr will provide some research examples and projects of what we've done here at the facility. And then I'll wrap up with an outline of proposal prep and how you can work with us. We ask that if you have any questions, to please write them in the chat, and then we will answer them and have a Q&A at the end of the seminar here, or workshop here. So Jim, I hand it off to you.
Yeah, thanks, Joe. Okay, so I'm gonna, as the agenda entails there, talk about the science plan and overview. And I'm going to mention hybrid simulation that maybe some of you may be confused, but don't worry, it's something I'm going to define here. It may seem out of sequence, but it's well positioned here to be a little bit later. So what we are is I like to think of ourselves as a next generation and certainly a multi-user facility. And we perform or enable actually the users to perform transformative research. And to do this, we closely integrate numerical simulations and experiments, and the objective is to advance natural hazards engineering research education, and really to mitigate the effects of these hazards, enabling them the challenge of the community resilience to be achieved. And this is met by improving the concepts for renewal and retrofit of the built environment, exploitation, new emerging materials, some that exist, others that aren't existing yet but are under development, and those are the future. Development of innovative resilient structural concepts, economical design approaches towards natural hazard mitigation, so that innovation and economy is very important. And then development and validation of more accurate physics-based computational simulation models. In the end, what NSF likes to endorse is that experiments have a purpose, and they're very important. They enable you to acquire data, which we're able to provide the means to do that. But in the end, that information needs to evolve to where it eventually reaches practice, and this is usually through then having computational models that are developed. But in order for them to be accurate and validated, you need the experimental data. Let me continue with the science plan. So one of our focuses, I'll just say one, but we have others, and I don't want to get you discouraged if you're not into hybrid simulation. So don't worry, I'll entertain you with some other approaches, but we do a lot of multi-directional and at large scale real-time hybrid simulations. Again, I'll define this more clearly later, but this essentially combines physical experiments with computer-based simulations, and it's to evaluate the performance of large components and systems and their interaction. If you wish, you could think of hybrid simulation as being cyber-physical simulation. It basically is similar in concept. And our facility provides user-friendly tools that enables researchers such as yourself to readily utilize this advanced testing technology and algorithms to perform complex experiments. And to give you an idea, we had a researcher come and do 420 tests in 3 days, hybrid simulation using our tools, in which they looked at isolating very sensitive equipment and mission critical facilities. And so that is currently the record, in which we invite people to forthcome and use and perhaps break that record. So our facility enables researchers to readily perform I'll just give you some examples here. 3D hybrid simulations. RTHS is the abbreviation for real-time hybrid simulations of, again, I want to emphasize complex nonlinear systems. When you get multi-natural hazards, we're thinking about extreme events here. And so usually the system may go nonlinear, either geometry or geometrically or material-wise. So that we certainly could account for. And examples could be storm surge, wind, or earthquake. Those are the three that come to mind that NSF has really recently been dealt with, particularly the first one with climate change. And we use analytical substructures created with robust computational modeling. We've done this from the ground up, and below is just an example of a tall building at Leanne Cal. We'll talk more about that's subjected to multi-hazards here. We have numerous response modification devices that could be used that are in our lab or that others may bring as researchers, but we can integrate those into the simulation where if there's not enough of these devices that could physically be placed, and usually there's a restriction because a tall building may have 100 of these, and of course you may not have 100 on your hands, but we can numerically model some of those devices and use model updating so you can accurately get an assessment of the overall system and how those devices modify the response of the system by using this model updating in conjunction with the physical model devices. And the other aspect, and you'll see some examples, and I can't overemphasize this, that multi-directional experiments are very, very important. If you don't consider them, I think you're missing out on some golden opportunities, and particularly to compete for funding. Multi-directional is something you want to mention here, and we can support the quasi-static testing, hybrid simulation, HS, or the real-time using these approaches here that involve nonlinear kinematics of the actuator and specimen motion. So the actuator may displace at a arbitrary angle, not be regularly aligned, and so that involves some nonlinear kinematics. And so, Dr. Ali may will show you an example of that in which she did some multi-directional floor diaphragm timber subassembly simulations. So in addition to that is the nonlinear analytical and the experimental substructures. And very important, any test you do, whether it's hybrid simulation, as you probably could appreciate, or quasi-static, you need to have accurate control of how you're imposing the motion to that structure. So I'm just going to mention this as being precise hydraulic actuator control. When you look at real time, it has to be done in real time. And so we've worked on that for a number of years and have been able to successfully do that. And we always monitor that when we do a test to make sure that we get accurate actuator control is very, very important. What are some of the key questions that could be addressed through the research that you say perform on our facility? Just may give you some research ideas. One is to develop an implementation to practice new natural hazard mitigation strategies and innovative resilient structural systems. So there's a little bit of vague, but it's at the top level of what a proposal may be looking to achieve as an objective. I think some other things that needs to be considered is enhancing our understanding of response to multi-hazards, accounting for soil structure interaction and also fluid structure interaction. You find when you look at soil structure interaction, the whole picture changes. It can have it could be an impediment or it could be an advantage, and it could change the behavior that really needs to be accounted for. There's a comprehension of the system level effects on the structural, non-structural components through these large simulation. And I don't know if you realize, but sometimes the non-structural components are of greater financial value and monetary value than the structural components, and the structural system may be condemned simply because the non-structural components don't continue to function. So non-structural is very important as well. Now, again, I'll just emphasize computational modeling. You can acquire high quality experimental data. We'll talk about some of the instrumentation aspects later, but this will enable you to, if you get the right type of data, we always offer some suggestions when asked, and how to develop the improved computational modeling by seeing what data you need to do that. Usually it's force deformation. And the outcome of this is be able to predict community infrastructure resilience, right? Where these response modification components are integrated to alleviate natural hazard effects. Also, training the next generation workforce natural hazards is important. Natural hazards engineering, in fact. This is through research and ECO activities. So when you write a proposal, you want to think about some of these aspects because the National Science Foundation does consider these to be important. So what are some examples of potential research projects that could be performed? These are actual, others are just visionary. One is autonomous semantic control devices, for achieving resilience in multi-hazards. You can think of an approach such as hybrid simulation in real time, since they may be rate-dependent devices. Could look at advanced bracing systems that integrate shape memory alloys into them for achieving multi-hazard resiliency. There you may look at characterizing the components, the alloys, or perhaps other components of the brace, and then doing hybrid simulation in real time or slow down to look at system level response to natural hazards. On the other hand, you may be wanting to advance computational modeling of reinforced concrete or complex loading histories. So there you would perhaps consider some quasi-static characterization tests, as well as multi-directional mixed mode controlled hybrid simulation to get these complex loading histories. Looking at quantifying multifunctional floor isolation systems through cyber physical testing. This is something that would involve real-time hybrid simulation because of the rate dependency. We have, again, like multi-directional floor isolation systems, non-structural components of systems which minimize the multi-hazard losses. It could be cladding or piping systems, say in buildings as an example. And there we can look at hybrid simulation and real-time hybrid simulation. Mentioning again soil structure interaction, the effects of that are very important in the interaction that it has on performance, particularly of tall buildings with supplemental damping outrigger systems. These foundations that these systems are tied to could have an influence on the effectiveness of the systems of performance, since these supplemental damping systems themselves typically rate dependent. You will probably have to consider real-time hybrid simulation, and Lee and Cal will show some of the actual examples of some of this later here. Symmetric controlled cladding is also a potential topic that Leanne will talk about as well. We have also transportation systems that the NSF now does entertain and accept proposals associated with transportation systems. Some of these, of course, will be highway type systems, bridges, and the response to multi-natural hazard. That could be earthquake, tsunami, storm surge. Wind probably is not too much of an issue, although it could be perhaps for taller type systems and cable stay bridges where the cables tend to oscillate and fluctuate from the wind loading due to vortex shedding. We also have fire that's now also being accepted as a valid research topic by the NSF, and you can consider some performance-based engineering research questions that need to be addressed. There you'd use hybrid simulation for furnace. We'll talk about some of those resources later. And then looking at response modification devices in buildings, again, considering the soil structure interaction. So it's a little bit redundant compared to what I maybe already mentioned before. And then finally, looking at coastal infrastructure, this has become more on the vision and the target of many entities. In fact, the federal government's been asked to respond to the climate change effects, and that usually is concerned with the coastal infrastructure and the inundation due to storm surge, and of course with earthquakes would be tsunami. And most of these are real-time hybrid simulation involved, but we also have other techniques that we'll show you here, so don't get discouraged if you're not into hybrid simulation. So let me begin then with the description, and we'll get to some of these other techniques here in a minute. First, give a little bit of history. We're a former NHERI site, so we've been around since 2002 is when we were first awarded our grant to create the facility. It's actually built upon an existing facility I'll get to in a minute, and then the lower right, you see a picture there, a photograph showing the multi-directional reaction wall facility exists within the Atlas facility. That's a little lower on the far near end of the lab here. So we were initially a multi-directional real-time earthquake simulation facility, and we've then graduated and advanced to other types of natural hazards. But I want to mention very unique in that we have a portfolio of equipment, instrumentation, infrastructure, test beds, simulation, control protocols for large-scale multi-directional testing. And what's not listed there, but may come up later, is also the experience in the staff. If you can operate this without having an experienced staff, both in the laboratory as well as in the strategic planning and operational aspects. We can host concurrently multiple large-scale experiments. So unlike a shake table facility, I'm not being critical of such a facility, you have one experiment on the table. We can have multi-projects in the lab. You can see a photograph of that on the right there. It was pretty crowded, but we managed to do that and host all those projects concurrently. Mention the experienced staff, that's very important. And also I mentioned Atlas. The Atlas Center is Advanced Technology Large Structural Systems. It's a former NSF sponsored center, but we've graduated from that, but we continue to operate, and that offers a lot of resources that we can leverage with our NHERI resource. NHERI, if you don't know, it's a natural hazards experimental research infrastructure. That's a community of experimental facilities operated by NSF. So our niche is we have an Atlas facility that offers many resources in addition to what we already have under the NHERI. We'll see some examples later. So the Atlas Center, this is the outside of the building. It's a large experimental facility. On their website, you can see the floor plan if you wish later, but inside here, I'll describe some of the approaches that we take towards testing here. But if you're coming to our facility, come to one of our in-person research or workshops. This is see as you enter the facility. So the people are, as I mentioned, very important. We have expertise on a lot of levels. I'm actually a registered professional engineer, so I'm very familiar with practice, particularly in California, where I'm registered. We have a number of other staff as well that are professionally registered. In addition, we all have a lot of us have industrial experience, so we're really in touch with reality, if you wish. We have expertise in structural engineering, earthquake engineering, geotechnical engineering, aeroelasticity, wind engineering, hydrodynamics and fluid structure interaction, probabilistic-based modeling, structural monitoring and damage assessment, and also coastal structures and inundation from storm surge and tsunami. We'll be adding a new faculty member to our group there. It would be Claudia Reich, who's currently a postdoc at Oregon State University. Her expertise is in coastal structures, inundation from storm surge and fluid structure interaction. And we're pioneers in real-time hypersimulation. We didn't invent the topic, but we've tried to advance the topic. I'm going to give a lot of credit to Steve Mahan, and also our colleagues in Japan originally developed that. Steve Mahan advanced it, and then Professor Nakashima then did some of the first real-time hypersimulation. We built upon their developments and then advanced the technique here to where we use it on a regular basis. That was our motivation. And so we have a lot of know-how in large-scale experimentation, including this approach. Also, a strong tie to industry, because we're registered professional engineers, but we also do a lot of industrial testing. So we have a lot of knowledge about what is important that the industry is looking at in terms of that and the passing engineers. And we're familiar with the codes and the standards, having contributed towards the development of those codes, and being also registered engineers, we get to be aware of those standards and those codes. And I'm mentioning in the laboratory staff, and we've had some laboratory staff here for over 30 years, and they're quite skilled with, we can basically build anything, steel or concrete or timber, whatever you want, or we can deal with outside vendors that manufacture these, but we have a good relationship with them. So with that, and if you have any questions, put those in the chat. We'll come back to those. Let me describe the experimental protocols in the facility resources here. First, what is hypersimulation? Maybe some of you know, but maybe some of you never are wondering about it, since I've mentioned it a few times already. And let me just give this by an illustration and an example where we have a very tall building, say 40 stories. And I'm interested in looking at the response of this structure under multinational hazards, particularly wind and earthquake. So this is the outside shell. You know, we have cladding or the facade that's going to absorb or have wind pressures exerted on. So that certainly would be of interest. The building also has mass, so in an earthquake, I don't show it yet, there'll be some concern here. So we're going to look at the structural system. Let's consider it to have an outrigger system, which every, say, 20th, 30th, the 20th, 30th, and the roof level, you can't count the floors, but those were where the outriggers would be positioned. And it'd be nonlinear viscous dampers would try to improve the behavior. Maybe there'd be other response modification devices added, but let's just look at the nonlinear viscous dampers are rate dependent. So for this initial and for this description, we're going to consider wind loads to be predefined, but they don't have to be. As you'll see later, what we can actually do fluid structure interaction where the wind is defined as the position of the structure evolves. In any event, if we want to look at the performance of the system, particularly these dampers, and you may not realize, but nonlinear viscous dampers, they're not really, there's models that exist, but the models are not necessarily accurate if the properties are changing, which in fact they do under more under earthquake than wind. But as a result, we're going to have to put something in the lab that we can't model numerically. So we're going to call that the experimental substructure. In this case, it'll be the dampers. And if we have a good model, numerically model, what we call the analytical substructure, we'll put that into the analytical substructure. So those components we feel relatively comfortable and confident can model accurately. We have the two domains, the cyber on the left and the physical on the right. And the input here, again, for this one example, the wind loading will be predefined, so it will come from an aerodynamic test, in fact, that we've done down at another site, the FIU site, in Florida International University, the WOW, Wall of Wind. We're going to have a simulation coordinate. So for each point in time, let's say at time I+1, we'll inject this loading, which is like a disturbance. On the right-hand side of the equations of motion is where that disturbance exists. So we need to integrate these equations of motions. They're multi-degrees of freedom. So they're actually vectors and matrices. We have the first term, which is the inertia, associated acceleration. The second term is the inherent damping, associated velocity. And the third and fourth terms are restoring forces. The first one has a superscript A is from the analytical substructure. These are restoring forces that will be potentially rate dependent. They could have inertia as well as dissipative characteristics from damping, but also possibly from just material nonlinearities and also geometric nonlinearities could exist. And then the last one with the superscript B is the experimental restoring force. And again, that could have inertia effects that would be basically existing in the lab, in the device itself. It could be certainly dissipating energy through damping, but also through material nonlinearity. But all these add up to where these balance equations of motion, and by integrating equations of motion, we can prescribe what I call command displacements to both of these substructures. There may be a transformation from the global degrees of freedom to the substructural degrees of freedom, but in any event, they'll be commanded to undergo these motions, really, or deformations. And what we want in return is restoring forces. And so these restoring forces that we get back, as you see there, what that does is it allows us to complete the integration of the equations of motion. In fact, to be a little bit specific without going into too much detail, the last step is to calculate the accelerations, where we look at satisfying the equilibrium. So all this has to be done in real time if it's a real-time rapid simulation. If you want to slow it down, which we can do, it could be slowed down and expanded time scale. But if you proceed in real time, you'll get the real-time structural response. If you're interested in another type of hazard, such as earthquake, we could replace the forcing function with the earthquake, which typically is predefined. If you want to look at fluid structure interaction, Lee and Cal will describe that later. So that's hybrid simulation. So why would we want to do that? Well, it's performed in real time. It's a simulation response, and hybrid is basically the cyber and the physical worlds where they're combined. So the cyber part, again, is well understood components. They're modeled numerically, and you could have various numerical substructures, analytical substructures for a given experimental substructure. The experimental part, again, is not so well understood, so it's something maybe new. that you want to incorporate into your research. It's modeled as a result and physically with the appropriate boundary conditions. This is very important. You want to be able to account for the appropriate boundary conditions so you get the proper interaction of the physical experimental substructure with the cyber or the analytical substructure. These are kinematically linked and they're synchronized in time. And you want to really consider full scale or large scale because size does matter. Example, heat is dissipative. The thermal mass is important there in dampers. And unless you do large scale, you're not going to account for that. You know, connections are important, especially welded steel, concrete. All that really should be done at large scale. So it's a very cost-effective method for that purpose. It integrates, as I mentioned, the numerical and physical aspects, so you get the best of both worlds. It allows you a comprehensive system and component response. What I mean by that, you can account for the interaction between the two. The other thing is, it's not mentioned, is you can dictate a realistic level of hazard. Example, in earthquakes, you usually have a hazard level, maybe say the MCE, max considered level, or you have a design level earthquake, or may have the more frequently occurring earthquake. You can stipulate that, or in windstorms, a mean return interval. You can associate your simulation with that and account for rate dependency. You can give some idea about some of the different types of capabilities I've mentioned already. Number of times hybrid simulation, real time would be large scale, as shown as the right hand side of this slide as a photograph, in which this is an earthquake simulation of buildings with dampers. You can see the multi-universities that participate, including ourselves. There's Cal State Northridge and Cal State Pomona. We have also large-scale hybrid simulation, which it's slowed down. We also have large-scale real-time hybrid simulation, in which we have multiple experimental substructures, and it's shown here again, participating with some of the external universities. Here we have 5 blue-colored actuators. There's actually 5 test beds here with different dampers located at different locations in the structure that is numerically defined. Now, we've also participated geographically distributed. This is just one of several examples. In this particular case, this is a transportation system. It was a bridge structure in which we participated with University of Illinois, RPI, which modeled the foundation under one of the piers and their centrifuge, and then we modeled another pier physically. There were 2 other piers modeled physically at the University of Illinois. So the superstructure tied all this together. The bridge deck was modeled at the Advanced Supercomputer Center at University of Illinois. That was a distributed hybrid simulation. This was not done in real time, but we have also done this in real time, in which I get to in a moment. But I want to just allude you to this ECI program that NSF, and you can go on the NSF website to get more information. You can look at transportation systems that you can consider some of these opportunities here. Another opportunity here, this is actually, I think, what Dr. Saunders did some of his work on orthotropic bridge techs. We have a lot of experience at the Atlas with bridges. Getting back to this distributed geography means you have located at different locations here. So the geographic, as you probably sensed before, it was different universities here. Again, this be done in real time. Lehigh and UIUC did some work here with UConn, in which we did some dampers that were semi-active, actively controlled. One was at Lehigh, the other was at UIUC. And the coordinator was located at Lehigh, but it was developed by UConn, operating real time under the auspices of Dr. Kim and Dr. Christensen, Professor Christian at UConn. Now, looking at other approaches here, you sometimes don't need to do hybrid simulation to research. You may just need to characterize a device. And so that may be predefined displacements or loading. And so that's could be quasi-static, or it could be in real time, but it would be characterization testing in any event. So here are some examples of an MR damper, symmetric control. Upper left, lower right, you don't see it, but that's a temperature-controlled chamber. There's a viscoelastic damper that was placed in that. And I show some other researchers, Professor Di Christensen and Spencer at Purdue, UConn, and UIUC. Myself, we were involved under a joint collaborative effort involving different projects, and then also another one, Professor South and myself, looking at these viscoelastic and viscous damping materials here, and dampers. And then we have also another one in which we're looking and participating with Iowa State and universities of South Carolina, that's U of SC, in which there's rotary friction device. This is a very important symmetric control device because the output has 100 times amplification of the input effort. So you put in a small amount of force in pounds, and you get kips out of this as a friction device. It's through this rotary technology here. And I think Leanne Cow will explain more of that later. Now, we could also look at characterizing large components, such as this coupled shear wall. This was done under the auspice of Gino Karama, Professor Karama, and Professor McGinnis at Notre Dame and UT Tyler. They did some of the work in our lab, and it also involves some advanced instrumentation with digital image correlation. You can kind of sense that from, you see the cameras on the mid-ground there behind the computers, monitors. We also have a fire chamber, if you wish, or furnace, in which you can do fire testing. It now is, as I mentioned, accepted by NSF. This is something in which you can build a furnace around your specimen. If you wish, this was a composite floor slab that was subjected to gravity loading, and the furnace was used to heat up the slab and look at the restraints through the connections to the columns and the effects that the slab have. And I can tell you that the steam was coming off of the slab from the heat that was projected underneath the slab. So it was assumed the fire was compartmental fire beneath the slab, and the data was used to characterize the performance of this. So again, you can look at the infrastructure, civil infrastructure from NSF for further information about opportunities there. Dynamic testing, another aspect here. This is characterizing the performance of multi-segmental piping systems and structures. So these piping systems distribute, the water that could be, of course, one of the functional characteristics of the system, but it could also be for the fire depression system. So this is a very important component of a building. And the purpose of these tests, it actually was initially sponsored by industry, but then we did some hybrid tests, was to look to see whether the system could perform under specified earthquake loading. So there's predefined qualification tests done, but then also some hybrid tests. And we found that the system actually worked pretty well for what was developed here. We looked at the connectors of these orange connectors between segments of the black part of the pipe, and also the lateral bracing that's in the foreground at about midpoint of each of these black segments. These are bracing the piping to continue to stabilize it. We also have a shake table. We can use it for conventional shake table testing, but also real-time hybrid simulation shake table testing. This is a project actually that Scott Harvey is from the University of Oklahoma has been using our shake table for looking at isolating equipment in mission critical buildings. And so here is a shake table that could operate in multi-direction. I think we'll get to some more of the details later. We also have tsunami, storm, surge, debris setup that we can do impact tests on that. I have a number of soil boxes. One of them is, this is the mid-range scale one, in which we can look at soil structure interaction, particularly soil pile interaction. In addition to that, we've also got a larger soil box and a smaller one even than the one I showed, in which we look at offshore wind turbine structures concerned aeroelastic hydrodynamic loading in conjunction with soil structure interaction effects. I'll get to this a little bit more later. And then now let's talk about our infrastructure. This, you've seen a picture of, this is our lab, I guess the day that it opened. It's never been as empty as it's been since then, which is a good sign. It means we're busy. See some of the dimensions. You can find more of this information on our website, but we basically have a run here of about 100 feet along the length of the floor. That's a strong floor that also has a strong wall, and the wall steps down from about 50-foot height down to 20 feet over the span with those little black rectangular shapes. Those are tie down points. So first, some dimensions there, as I mentioned, 50 feet height. It's over distance of about 200 feet, and the width is 50 feet as well. We have 5-foot anchor grid points, so and 5-foot centers. You can tie down actuators or fixturing or your specimen. The strong floor, as I mentioned, the dimensions that it's actually 40 by 100, again with this grid layout of 5 feet. It has a hydraulic supply system that includes an accumulation system that could provide very high flow to simulate very large demand on components such as earthquake or sustained wind. We have over 30 hydraulic actuators that the Atlas facility could leverage our NHERI equipment. We have digital servo controllers in addition to data acquisition systems, a large array of conventional sensors, and also image correlation systems. And of course, we need something to be able to lift specimens and equipment in place. So we have, auxiliary equipment such as a 40 kip crane, and of course forklifts and man lifts, etc. Now the hydraulic power, this is provided by NHERI. So that initial Atlas was the infrastructure we augmented with our hydraulic power and actuators. This allows us to, as example, simulate real-time large earthquake demand in excess of 30 seconds. So this accumulation system that we have provides additional power, hydraulic power, to our pumping system, which is 5 120 GPM pumps. And so we can, for instance, get over 4,000 GPM. We've actually tested our 5 dynamic actuators. Each of those has 500 GPM servo valves concurrently. And some of the details of those actuators, you can see the capacity. They're in English imperial units. If you want to convert those, I think it's over 2,500 kilonewtons, but 500 kips, roughly, and about 380 kips are the 2 actuator sizes. The stroke is plus or minus 20 inches there, so about a meter in total stroke. The maximum velocities are 45 inches and 33 inches. If you need to go fast, we can actually add another servo valve, but this is sort of the standard here. The valve attached to the actuator shown here on the lower right. The pumping is in the middle of the pump room, and the accumulator is on the right, and the distribution system runs around the lab in the upper left photograph. And I mentioned servo valves. We have 10 of these, so we can position them around the actuator as to where the demand needs to be met by the supply of flow. Now, I mentioned we can do concurrent projects. These are just some evidence of that. We have some large-scale semi-active controlled paneling and high-rise structures which have outrigger systems, and so we have 2 test beds of real-time servo control of nonlinear viscous dampers. Same time, we had a spine system with these connectors between the spine system, which avoids soft stories in these frames, such as moment-resisting frames. Under earthquake loading, that was done concurrently. The DIC system is shown there, projecting onto this connector, which is in the foreground. Multi-directional timber structures were tested for tall wood buildings. Dr. Amir will talk more about that. And then we have a collector system which collects seismic forces and is on a load path to disperse those into a lot of load resisting systems. That's something where testing is ongoing, and the layout is shown in the foreground here. So all these are actually in the lab concurrently, projects going on concurrently. Now we have an integrated real-time control system that enables a lot of this, and we configure this to wherever the experiment is set up, that the controller will operate and control the actuators accordingly. So the details are shown here. This is described more in detail in our website as various components, but it allows us to configure a test for the researcher. We can configure these to basically in the mode of the processes that I showed for the different forms of testing. So the servo controllers talk to the simulation coordinator, and it talks to data acquisition, and then also for the cameras and the remote the remote cameras and the participation are all within this integrated control system, and it interfaces with the servo hydraulic system, which controls the actuators and the feedback for data acquisition. So we can configure this to run in real time, as they know, I mentioned. But we could also expand the timescale to slow it down for either hybrid, distributed hybrid, or just for quasi-static or characterization testing. It does not have to be in real time. It could just be one component. It doesn't have to be a subsystem or a complete structure. Now, we've also been able to distribute hybrid simulation. We could virtually connect to almost anything. Tommy Merla's expertise is in the cyber physical, the IT aspects in particular, and we've been interfaced, of course, with Open Fresco and run Open Seas. We have our own software to do a lot of these things, but if you need, we can use Open Seas, Open Fresco, or any customized software. We, of course, want to interrogate it, make sure it doesn't cause any ill effects, but we've integrated that with our IT architecture. And it's a very flexible design, so we can have software and middleware packages that are developed by users, or the CI, the NHERI cyber infrastructure component of the NHERI network. These can be plugged and utilized for testing. Of course, we're going to have to assess that and make sure that things are connected properly, but we've managed to do that, and we'll continue to do so with researchers. Some other resources and combinations, we can prepare specimens, or we can manufacture, or should I say fabricate those on site, or you can have them manufactured, say, as a steel component offsite, it be delivered, and we can then, add whatever needs to be completed to that, or put it in position. Concrete, you've actually, poured, in timber, we've actually construct that as well on site. We have mechanical testing capabilities. That's very important for material testing. In an auditorium, we have ECO activities, and provide then educational opportunities to the audience there. So I mentioned our staging. We have also a machine shop. We have various laboratories, intelligent structures, mechanical testing, well, the adjoining materials and microscopy, and offices that if you come to visit us, either as a researcher for a planning workshop that you'll see in our webpage that you could consider coming to, or if you're doing research here, we have offices we could provide to the visiting faculty and their students, but also staff and visiting researchers, that would be, say, the students or the faculty. And of course, meeting rooms, I mentioned the auditorium. We also have conference rooms that we hold webcast and Zooms, and just regular meetings in. And we have ability to store things, and it's a secure environment. Facility is locked up at night. We have security come through, and we've got webcams. Not that we spy on people, but it's a secure environment. Now, our webpage is very important. I encourage you to visit it. This is not the most recent news, but here you'll see the virtual workshop that you should have registered for, the one that's today. We have also, I want to mention, small group researcher workshops. You should go online and look at these, because this provides some support for you to come and visit our facility, maybe get some hands-on experience in operating, see some of the equipment being operated, and how real-time hybrid simulation or just conventional testing is done. And you can even do some pilot testing to getting data for a proposal. The other news here is this creation of a cyber physical that we'll describe here a little bit later. And there's some videos that you can look at as well. Other resources, these are good for proposal preparation. There's numerous documents here. Some of these you can integrate directly in your proposal, such as equipment facilities, and also the data management plan. You may want to update that a little bit for your own data you'll collect, but the responsibility of costs are laid out there that I think Joe will talk about a little bit more later. Dr. Saunders, test beds and science plans. We're actually updating this, but this is sort of a living document that continuously gets updated. So talk briefly about the test beds. We have some test beds you can use. Lateral load resisting frame test bed. This is showing the height and the width. And in here, we tested many lateral load resisting systems, both primarily unidirectional, but also multi-directional by taking out the front of this. This is a red frame that basically is for bracing the unidirectional, in this case, moment resisting frame that was tested, or brace frame that was tested. We have the non-structural component simulator. We can test non-structural components, and here we have a suspended truss system that serves as, say, the ceiling from which we suspended the piping system. and subject that to multi-directional motions. I think Leanne Cal may talk about this, but if not, this was pressurized piping that was subjected to multi-directional earthquake motions. Multi-actuators, these are the capacities that I've already mentioned. These are now also in kilonewtons. I had to correct myself. It was 2,300 kilonewtons, not 2,500 for maximum capacity of some of the actuators. And then the Cyber Physical Simulations Laboratory, CPSSL, this provides a couple different resources. One is real-time test bed. You see some examples here on the right and some friction rotary damper characterization test results that were achieved in that facility. This is about 4,000 square feet, and it's been created for a couple of reasons. One is, of course, to enhance the research, but also the ECO, that's education, community outreach, and researcher training to enhance the experience in cyber physical systems. Some of you may not have any clue, others may be quite versed, and we could help and provide information for people of various backgrounds. And the goal is to broaden the user base of our facility. And so one way to do this is to offer small scale, lower cost experimental test beds, but also create more hands-on opportunities for cyber physical testing, give you some ideas how you use our facility to meet your researcher needs. It's very efficient for performing capacity building pilot studies. For instance, we're doing fluid structure interaction, soil structure interaction, developing many new capabilities, and also researchers have come and been using them for pilot tests that look to then write proposals based on the data they achieve. These are some of the actuators we have here. There's various models that may not mean much to you, but I'll list the capabilities below here. But we also have electric actuators for controlling semi-actively some of these devices. And I think most important, we have an independent integrated control system, an acquisition system that's identical to what I briefly described, an integrated control system. Same software, same hardware, so separate system, but we could link the two together if you wish. But anything we develop in the main lab is transferable and vice versa to the cyber physical lab. And these are some of the actuator capacities. They can go pretty fast. These actuators can go up to 51 inches a second. We've got some other a little bit slower actuators, but they're relatively fast, and they range in capacity 55 down to 11. If you need larger capacity, of course, we go to larger actuators, but these allow you to do some smaller but realistic tests here for your research or just pilot studies here. So we have also the multi-directional shake table created for the same purpose here as Dory described. Very efficient, as I mentioned. This just shows some of the vision here. This is looking at floor structure interaction, FIS, and not fluid structure interaction of a test bed where we have a shake table and they have equipment that's in mission critical facilities. Mission critical means that if the equipment were to go down, that means either your traffic ticket that is sitting there if the FBI is gone, you don't have to pay it, or your financial data that you have or your medical data that's on the computers may be lost, which is not what you want. So that equipment needs to be preserved, and whatever natural hazard event is imposed on that, particularly maybe an earthquake, could be maybe a severe windstorm. And so, we've been using it. That's one of the applications. The specs are noted here. They're also on our website, but we have digital control that go up to even maybe faster. Tommy could answer the question later, but I think it's even 4096, but 2048. We certainly can use. We can use 1024. It's got a payload of 13 kips at 1G. The plan size is 6x6, and got a plus or minus 7-inch motion in one direction, 10 inch the other, only because of the actuator that we currently have attached to it. But they can go up to 51 inches a second and 20 inches a second in those two directions. These are X and Y horizontal directions. The tie down points, I think, Leanne, are at 6 inches. You can correct me if I'm wrong there. And there's a lot of tie down points, and we can be used for hybrid simulation in real time, or just quasi-static testing. We can configure that, use it as just a load transfer mechanism, or if you want just conventional shake table mode. And so it's very versatile. We're actually looking, and we're adding a third component, which is the third one is a vertical direction here, but that's still in the works. But right now we have translation, and also rotation. You say, well, that's weird. Why have rotation? Well, think of this. If you're looking at a non-structural component, you may be a structural component sitting in a building or a bridge. I guarantee that structure on that floor or that bridge has translation plus torsion, because nothing ever is completely concentric. So if this were, say, on the building floor of some location, you're going to have that torsion. That torsion will add accelerations to the components. It's important to consider. Lower bottom is just showing multi-directional response to the motions on the lower left, and the lower right is a base shear versus the translation in one direction for this isolation bearing. Tsunami debris, we already talked about. It's got a high-speed cameras acquisition system, high resolution load cells with high bandwidth accelerometers and laser displacement transducers. We do soil box. There's two different sizes. These are flexible designs that could be rearranged, stacking them to be a little bit taller, but they're 6 by 6 by 6 foot and a 6 by 6 by 3 foot. 3 foot is the height there, so we'll be up to 9 feet tall here. It's got actuators with acquisition systems, sensors for soil and foundation measurements, and advanced sensors are amongst those with digital image correlation. And this just shows a schematic of that with the drainage there. So you get a drained and undrained soil. We also have a large scale soil box. This is under the auspice of Professor Mohammed Suleiman, or soil structure interaction expert at Lehigh here. This is, I think, up to 15 feet high, or almost 20 feet in height. It's got the actuators, actually 6 actuators, multi-directional acquisition system, soil sensors and foundation response measurements, digital image as well. And this is being used also for offshore wind turbine testing. So we're looking at soil structure interaction with both floating and fixed monopole type systems, in which we have some components in the soil box for either just characterization testing of that or as a hybrid simulation. And this shows a hybrid simulation configuration we've been doing here, in which on the left side, the experimental component is the foundation embedded below the mud line, and everything above that is analytically defined in the analytical substructure, including, in this case, the monopole, the tower above the transition piece, and also the blaze of the turbine. That's the analytical substructure, considers the fluid structure, aeroelastic effects there. So that's based on the display position of the wind. That's through a simulation coordinator that integrates that and ingests experimental substructure. We have that furnace I mentioned, that include digital image correlation under heat. We have a special system for that. We have a number of these digital image correlation systems. In fact, I think we have now 5. The systems reconfigurable, I mentioned that. So I'm now going to hand this over to Leanne Cal. I may have gone over a little bit, but I'm handing this over to Leanne. And I think, Leanne, you have your own set of slides, so I'm going to unshare and you can go ahead and do the sharing.
Okay, thanks, Jim. Okay, can I see my screen? Okay, good.
Yeah, you're good. You're good. Oh, you got to swap to the other screen. You're on. Yeah, you're on the presenter.
I mean, how about this?
Yeah, it's better.
Okay. Okay, good afternoon, everyone. So my name is Liang Kao. I'm the NHERI Lehigh research scientist. So today I'm just quickly go over some example research projects conducted at NHERI Lehigh facility recently. But here's the list of the recent current project at NHERI Lehigh facilities. So it covers multidisciplinary research areas, right? And including different type of structures, such as tall wood structures, steel structures, reinforced concrete structures. So the I highlight 5 as yellows. So this 5 projects I'm gonna talk about in details in the next couple of slides. So for the rest, for example, we had a project from Colorado, studied the resilient-based seismic designs for the tall wood buildings, and also a project from Princeton studied the shear buckling mechanics for enhanced performance of thin plates. And also University of Arizona, we studied the performance of seismic collectors. So these three projects are utilizing our high bay lab, and then they are trying to conduct different type of methods such as multi-directional, quasi-static on the tall buildings, quasi-static on the shear bucklings, and also including the hybrid simulations on the seismic collectors. They also gonna utilizing the DIC system to measuring the shear strength, and also we have a project from University of Illinois to study the frame span systems with force limited connections, which is a new type of energy dissipators. And also we had the soil structures we also have the a research project from soils aspect to try to study the development of innovative ultra high performance reinforced concrete foundation systems. So we had recently had a research project from University of Virginia to study the new type of self-centering seismic dampers, and also the external researchers from Harvard to study the damage detection localizations methods. They got also utilizing the damper tests that we described before, and also some type of DIC systems. The test method will be doing quasi-static testings and real-time hyper simulations. So notice the 13th of these 20 funded projects are from the external researchers, and also including the 3 recent career reward. You see Scott Harvey from University of Oklahoma, and Austin Downey from University of South Carolina, and Barbara Simpson from Oregon State Universities. They both conduct the pilot studies in Lehigh facilities and got career rewards. So for the next couple of years, they gotta do utilizing our damper test bed and the CPSSL lab to conduct some characterization testings for the isolators, and for example on the Scott Harvey's projects, and also our real-time hybrid simulations. So now I'm gonna go over 5 projects one by one. So I highlight in the list of tables. So the first one is a collaboration research between Iowa State and Lehigh's. We try to develop the semi. So on the Iowa State universities, the overall view is to improve the performance of buildings utilizing a controlled variable friction cladding panels. So which the natural hazards we targeted is earthquake and wind, and the wind force can be alternatives from NHERI FIU facility and University of Florida facilities. So the scope is try to develop a new type of cladding connectors and to conduct the characterization testings and perform large-scale real-time hyper simulation to validate the numerical models. And on the Lehigh side, we are trying to our overview is to improve building performance using the passive energy dissipate connectors, combining with supplemental damping systems. Still, we are tilted to the multi-hazards. Our scope is to try to develop a prototype buildings with various height and the performance nonlinear time histories to assess the performance, and then also perform a large-scale real-time hyper simulation to validate the model and results. So here we developed a prototype building. This is a 40-story building, as Dr. Rickles mentioned before. It was designed by the SGH, and it conduct BRB frames in the middles, and then 2 outrigger frames in the east and west directions. So the target is try to run hybrid simulations, installing different type of supplemental damping systems to tilt it to the multi-hazards. Because of this specific configurations, we installed 12 viscous damper, nonlinear viscous damper on the outrigger columns on east-west directions. And we also utilizing 1 existing physical dampers in our lab as experimental substructures. We assume it is located on the 40-story, the top floor. And also for the rest of 11 dampers, we model it numerically using a nonlinear explicit Maxwell elements, and also we using the real-time online model updating from where we can get input from our physical damper to update those dynamic properties of these numerical dampers. So these key structures have near 7,902 degree freedoms and then nearly 3,000 elements. So before we conduct the hybrid simulations, we did a characterization test on these physical nonlinear viscous dampers. Here is we have a harmonic displacement input to this damper. We're measuring their force deformations loop, which indicates their energy dissipations. We try different frequencies of this input, and you can see the damper force is highly dependent with the velocities. So which just means we have to do the real-time hybrid simulation, because any slow hybrid simulations, you won't be able to capture in the actual stamping force and the dynamic. So this is the 3D real-time hybrid simulations videos showing this buildings equipped with the nonlinear viscous dampers subject to the ground motion MCE levels earthquake. And you can see the right graph is plotting the north-south and east-west displacement, and then and also the ground accelerations. And the top one is showing the roof displacement on the top views, and then the next two graph is the first story BRB frames on both north, south, and east-west directions. And you can see during the earthquake, the buildings develop a high mode, and then all BRB frames had nonlinear behaviors. So it indicates the BRB frames start to yield. And the bottom one is actually the damper heuristic, capturing from the experimental substructures on the right will be the damper force and the displacements. You can see this nonlinear behaviors indicate the energy dissipations by these dampers. We also do studied on dampers, steel building performance and wind load. First, we developed the aerodynamic building models, which is 1/150th scale models, and then we install them at NHERI FIU facilities to obtain the wind pressures time histories distributed on the buildings. Second, because we only have outrigger columns on the east-west there, on the east and west side, which is where we installed this viscous damper, can be affected on the east-west directions vibrations. But on north-south, we try to install two mass friction dampers on the roof to reduce the accelerations under the wind load, where we also utilizing a new type of symmetric dampers we call boundary rotary friction dampers, which will be another experimental substructures for these hybrid simulation studies on the other directions. Here, this is the videos we conduct under the wind loads. So the wind load contains about 6 minutes. So we speed up these videos, but we did do this in the real time. And you can see this wind is actually blowing in the 45 degrees. And then if you look at the top roof displacement, there's a vortex sheddings happens in there. So it indicates the importance of running tests under multi-directions, because if you only do the 2Ds, you're not able to capturing this vortex sheddings. Of course, under the wind load, all the BRB frames behave linearly, but still we are modeling using nonlinear elements. And then the bottom two graphs, the top one is the friction dampers heuristic, and the bottom one is the viscous damper. You can see the friction and the viscous damper have total different nonlinear dynamic behaviors, which is also hard to modeling numerically. So that's also highlight the benefits to running real-time hybrid simulations. We just don't have to model in this. So here's the quick result. The major finding is nonlinear viscous damper in outrigger system combining with the TMD can be effective in improving multi-hazard performance of tall buildings. You can see it can significantly reduce the wind and earthquake maximum acceleration around like 30%. and attention must be given to prescribing sufficient damper stiffness related to that of members in the low pass. So, sorry. So after that, we note under the wind load, we're only utilizing the aerodynamic models. So next, this project is a collaboration project between the Lehigh and FIU facilities. So in here, we try to develop a new 3D real-time aeroelastic hybrid simulation technologies to understand the effect of wind structures interactions. So instead of building aerodynamic models, we built a new aeroelastic models in the FIU facilities, where the entire buildings is controlling by the 2 electric actuators and with a base turning rotational centers on the base. So all these simulation coordinators will give a command displacement to the experimentals, to the aeroelastic substructures, where those 2 electric actuators will make sure the buildings can move as needed. And also we're also utilizing a new small type of dampers, where we're adding another experimental substructures. Means we're not only able to do the real-time aeroelastic hybrid simulations, we can also adding a physical dampers to retrofit the buildings and for the natural hazard mitigation purpose. This is 2 major improvements with what we did. And also because these comparing with conventional aeroelastic model, all these structures properties are built in the analytical substructures, where it's modeled in the computers. So we don't have to model any mass stiffness in the aeroelastic model, where we can put all the pressure type around the buildings to measuring the real-time pressure distributions on the buildings. So here's the videos of these testings. Those buildings is 1/150 scales, and then to do the hybrid test, we have to scale it the time. The time scale is 1/14. Means 1 second testings in the wind tunnel lab representing 14 seconds winds in the real life. And then for the analytical substructures, we're using 2-degree freedom systems only mimic the roof, because the building is only able to move. Sorry, the building is only able to move. We only targeted the roof building because the aeroelastic substructures is kind of is a rigid at this moment. So you can see under the wind load, there's the structures behaves linearly, but because since all the dynamic properties are modeled in the computers, we are definitely able to modeling nonlinear elements, which will be considered as the future research. So here's the major findings comparing with the aerodynamic models. So we found out some cases showed a significant change in the mean CP values after considering aeroelastic effect. For example, on the windward side, when we look at the wind pressure distributions, we found out there is up to 40% change on the windward directions, where you can see from the contour plot, which can be significantly changing the wind designs on current design code, because all these parameters are basically coming from the aerodynamic models. But when you consider aeroelastic effect, there's definitely a big change on the wind design. For the next one, we are going to talk about we're also adding the soil structures foundation systems, which is where we also adding the soil structure interactions in these 40-story buildings. We are, instead of using 1,000 degrees models, we are actually using the neural network to representing the foundation systems to fit in. We also did the studies on both earthquake and wind studies. So for the benefit, we using a neural network based method trained using machine learning to study the soil structures interactions effect. Instead of by comparing in this case, we only did in 2D models. So by comparing with 2D OpenSys models, which is using 1,000 degree freedom to represent the soil, you can see when we are adding a neural network model, we're only using four-layer neural network models and 8 inputs and 8 outputs. So which significantly reduce the degree freedom need. So we can perform the real-time hybrid simulations. We also did a study first to comparing the neural network model with the OpenSys model. You can see on the right corners the time histories. Both our neural network model, trained neural network model predicts matchings very well with OpenSys models. So that means these neural network models can be represented to the soil structure interactions. And here's the major findings where when we study these 40-story buildings under the wind loads. So we look at the roof displacements with and without soil structure interactions. The red curve is without soil structure interactions. You can see that's almost, so we almost have a double the roof displacements. There's a significant difference instead of because not all the structures that's never sitting on the solid reinforced concrete, right? It's always sitting on the soils. So the soils, the structure interactions is really important. So the next one is from external researchers, Scott Harvey's, the University of Oklahoma. They try to investigate the multidirectional nonlinear dynamics of floor isolator systems. Where you see this, the right picture is the floor isolator systems. There's 4 rolling pendulums, and those systems are designing for to protect non-structural components, and their purpose is try to utilizing our facilities to investigate the performance of this isolator system and then evaluate design methodologies for this rolling pendulum bearing systems. So in here, we perform a large-scale characterization test first to experimentally validate the physical-based mathematical models. We also perform large-scale real-time hybrid simulation to quantify the performance of these isolators. So we put those isolators, floor isolators, on our shake tables, and we also adding 2 red beams to mimic the non-structured components weight. And we also installing the 3 restrainers because in this case we're doing things upside down. So normally we let the top carbonate not moving but moving on the bottoms. We're also using the 3 load cells to measuring the damper force from the isolators as well. And because of this damper, this shake table is able to providing multi-direction directions, including rotational. Is ideal. Is fitting the needs for this floor isolator systems. So first, here's some characterization test results. So we did multi-directional characterization test, and here's we're only showing one directional normalized shear and displacement. You can see under different frequencies, there's a total difference dynamic behaviors. It indicates the need to do the real-time hybrid simulation because the rate dependencies. So here's the hybrid simulation scheme. So we select the structures of interest and also the non-structured components such as several cabinets on top of the isolator systems. We numerically model the structures in the analytical substructures. We also had this 3D several cabinet models, numerical models, where because this model is not connected with structures, but the behaviors are embedded in the structures. And the physical experimental substructures will be the floor isolator systems. So once we studied earthquake, once the simulations coordinate receives earthquake ground motions input, it generates analytical commands to the analytical substructures, experimental command to both the physical isolators and the 3D carbonates models. And then we receive the restoring force from both, and then to calculate the real-time hybrid structure response. So here's the quick videos for this. So you can see the top 3 graph will be the 2 directional normalized restoring force capturing from the floor isolators, and then the pendular deformations of the top views. And then the bottom right is the experimental vertical displacements with the friction pendular motions. You can see the concave concave shape indicates the dishes of rolling pendulums. And then we also plot the floor total accelerations with equipment total accelerations. You can visually see the difference when you're adding floor isolators. You can see the equipment's total acceleration will be significantly reduced. So here's the major results. So by installing the floor isolators, we are able to achieve almost 81% on one directions and nearly 70% on the other directions. It's showing the effectiveness of these floor isolators. So the last project is the project from the Southern Methodist Universities. They developed a new type of predator sand dampers. This is a new type of passive dampers. Their purpose is characterize dynamic behaviors under different type of temperatures and perform hybrid simulations to study the natural hazard mitigation performance. So to do the various temperature tests, we first develop a mock-up systems, and then we utilize these wire type heaters. We wrap around on the cylinders, and we also use the thermocouple controllers to conduct controlling the temperatures. You can see the target temperatures, and then we also have a thermal couples, different thermocouples measured at different locations to study this. Once we're reaching the temperatures, we conduct a dynamic characterization test. So ideally for the dampers, the damper force is coming from the frictions between the piston rod and then the sand. Once we also give a pre-compressions to generate the pressure on the sand. So once the structure, the piston rod is moving, because of the pressurized sand, so the damper force can be significantly enhanced. So it will increase the energy dissipations. So first, we install the dampers to our facilities, the test beds, to do this dynamic behaviors, dynamic characterization test. And for next, we also studied these dampers on using real-time hybrid simulations, where we study single-story CLT structures. We install two dampers on the CLT rocking wall systems, and we assume this. So for this hybrid simulation, the two physical dampers are installed in our lab, and we assume these two dampers are located on the side of the CLT rocking walls. To capturing the self-center capability, we have pole tensions in the middle of the CLT wall, which is Alia gonna present later to talk about this CLT wall systems. So all these analytical substructures will be the CLT rocking walls, and we're using different type of gap elements to mimic the rocking of these structures. Here's the videos on the CLT rocking walls utilizing the sand dampers under the earthquake. So you can see the red graph is the two different dampers, the hysteresis loop of these dampers, and the left bottom one is the base shear force, the solid drift. Because the self-centering rockings, you can see this because the rocking it indicates the self-centering, and also adding the dampers enhance the energy dissipations. We're also comparing the base shears accelerations and the solid drift with the elastic wall system, where it's sitting on the fixed base. You can see there's significantly reductions on the base shear and then the roof accelerations. And the solid drift we have higher because we allow the structures to rock. That's the difference. Okay, here I'm gonna pass to Dr. Alias, and she's gonna presenting the next research project. Alia.
Thank you, Liang. Let me share my screen. Is it on presentation mode? Is everything okay? Can you see it?
Yep, looks great.
Okay, so I'm gonna present the projects that I'm actively involved with, and the first one is a collaborative project with the Colorado School of Mines and Washington State University. I'm gonna mainly present the work done at Lehigh, and the overall objective of the project is to investigate the resilience, the seismic resilience of tall wood buildings, and we have here the test sub-assembly, which still exists at our facility and can be used as a test bed for any collaborations with researchers. So it's part of a prototype wood building that consists of a rocking CLT wall, a floor diaphragm, the collector beams that collects the lateral forces from the floor diaphragm to the wall, and a gravity load system. And this gives us a better understanding of all the components or the structural components behavior under multi-directional loading, so we can impose in plane and out of plane loading on this test sub-assembly, and also we can have a bit like a more realistic performance of the building where all the structural components interact together under multi-directional lateral loading. All the components and connection details in the test sub-assembly were designed to accommodate the multi-directional displacement of the sub-assembly. And we had like a minimum story drift as a performance objective for damage initiation for the components and to the components and the connection details. And this sub-assembly was like subjected to probably more than 500 cycles of multi-directional loading, and we tested it up to 6% drift, and it remained undamaged and can be used in any time. So the complexity of this project was mainly that we wanted to control a large-scale sub-assembly, and at the same time with that has like a flexible diaphragm, and we wanted to impose in-plane and out-of-plane displacement to the sub-assembly, but at the same time we have the floor diaphragm is subjected to a vertical motion or drop because of the gravity column rotation. So we established a 3D kinematic relationship between a control node on the sub-assembly, and we had like a specific layout for sensors to give us a feedback in 3D, and also we had a kinematic relationship with the actuator command displacement in order to control the sub-assembly. You can see here a video of one of the lateral tests that we performed under multi-directional loading up to 4%. The red line is the target floor diaphragm, the story drift, and you can see how accurately we can control the sub-assembly and all the kinematics, the 3D kinematics of the sub-assembly. The other project that I'm currently involved in is a collaboration with Howard University, and the main objective of it that we wanted to use the vision-based sensors or the video cameras as our main displacement feedback. Instead of the conventional displacement sensors like LVDTs and linear potentiometer, and this will let us overcome all the limitations from the conventional sensors, like the extensive time and effort in calibration, mounting, wiring, all of this like limitation because of like the discrete points to measure or track the displacement, but at the same like on the other hand, the computer vision based tracking method will let us be able to track single point or multi-point or full field displacement in the saved frame. So and we are expanding right now a video tracking program where we are applying this method on current projects in the NHERI Lehigh experimental facility. And for example, this is one of the projects we were tracking the tip deflection of a cantilever plate, and we are comparing the feedback from different camera lens type and different resolution with the feedback from an LVDT, and you can see how accurately we can track it. And Dr. Rickles will now summarize the resources and capabilities of our facility.
Yeah, thank you, Ali. I'm going to go ahead and share, take the screen here, and what I want to do here is to just summarize, and then Dr. Saunders is going to then describe to you how you can go about taking advantage of what I'll emphasize here. So just in summary, in terms of the resources and capabilities, I'm going to emphasize something here about size. The size matters. And the multi-directional loading effects do matter. And this is something very important in terms of when you write a proposal and do your research, you want to be competitive. And there's a lot of research questions that relate to this. So you need to consider these aspects when you write your proposals. Just to give you some examples, Liang had talked about the wind loading on this structure. The wind was blowing in the northeast or the northwest direction there, and there's differential pressure that acts is not uniform around the circumference in addition to vortex shedding. So there's a crosswind effect in addition to this non-uniform pressure, which creates translation as well as torsion, and there's some higher frequencies that result from that. So this is going to change the response if you only assumed planar type motion and didn't consider the 3D effects here. And this was illustrated, I think, here quite graphically by Liang here. I think the other thing too is you saw this video and it was played back pretty fast. That test, I guess, Alia took a few hours, but Alia played it by pretty fast. But
Yeah, I was limited with time.
Yeah, no, that's okay. I think it's very effective. But what I wanted to point out about this is in the upper right-hand side, you see these panels, that's at the base of the wall, and there's actually damage that develops. And as has been stated already, the purpose of this work was to look at the damage that is accrued. And what we found when we went through and did this, and this was actually something that Dr. Sals, who actually is a collaborator on this, suggested that we consider the fragility. And so under multi-directional loading, when we generate these fragility curves, we found that the probability of exceeding damage limit states increases by maybe even more than a factor of 2 compared to the unidirectional loading. That means that everything that's been assumed on unidirectional loading is not necessarily going to be conserved, because under true earthquake loading, a building is subjected to bidirectional effects. And so there you likely get damage more than what you didn't account for if you ignore the multi-directional effect. So these are just 2 examples, but you could probably envision more. But what I want to note here is that we as a facility have some unique capabilities that you may not have in your lab, but we're open access. We can accommodate you to do this type of work where you need to consider the multi-directional effects. So we have the experience and the resources and the equipment to do this, and we could generate as a result some cutting edge research results that generate very important data. And I just want you to kind of keep that in mind. And so how do you achieve writing a successful proposal? Dr. Saunders will then give you the guidance on that. So Joe, I'm going to stop sharing. I think you have your own set of slides you're going to use, right?
Yep.
Okay.
I'll take it from here. Give me 1 second. Is that okay?
Yeah, look good.
All right, great. Yeah, so I'm gonna just briefly talk about how to work with us here at the Lehigh NHERI facility. Right, and the opportunities you have here, how we can support your proposal through the proposal writing stage, and then the award stage, and then actually executing the test here. So this part of the presentation here is just broken down into a pre-proposal stage, a proposal writing stage, and then the post-award stage. So I guess the first thing to mention here is that we are an open facility, and we're open to both public and private sources, right? So public being something like NSF funded projects, and private being industrial type projects. So our NSF funded projects that utilize the facility have specific costs. that qualify for funding, and they can be funded through the NHERI O&M operations and maintenance budget, and then the NSF project itself, while projects funded via non-NSF sources are responsible for all costs associated with the project. And so here's kind of a flow chart of how we'd go from proposal prep all the way through testing and then post-testing requirements. What I really want to mention here is that so we can help you write your proposal. We provide that service and help in writing an NSF proposal. We'll help you plan your project here at the facility. So if you come in here with some ideas, we can provide some help, both with additional ideas and then how you can utilize the facility. And there are a few things that I wanted to highlight here. I'll get into more detail, but that first phase 1, user training, that'd be your first step into the laboratory itself after we plan a project and do proposal writing. You'll want to make sure that you're trained in operations and how and what we're doing here at the lab. We're all researchers, so testing on phase 4 is the fun part. But we need to make sure that we're developing a good plan, like in phase 2, and have an idea of, what equipment we're going to use, who we're going to use, what expertise we're going to use. So we'll want to make sure all of that is planned out in terms of budget, schedule, labor, equipment. Then we get on to testing, and then finally, there's another important step, phase 5, which I'll talk about some more, is uploading raw data. So NSF, as a requirement of operating a NHERI facility, we need to upload all test data to a NHERI repository, and that's a really critical step, both for us for sharing that information and NSF. So I'll allude to that some more later. I'll talk about that some more later. I just wanted to highlight some of that. So first, we'll talk about the user proposal prep, and this is also in 2 stages, right? So we have the pre-proposal stage, just kind of interacting with the facility, coming to us and asking us kind of what we can do. This is a good first step, right? Attending the seminar, you get an idea of what we can do. I encourage everyone to review the NHERI Lehigh website for more information, and then we'd go into proposal writing, the proposal writing stage. I'll talk about that in some more detail too. So first, we have the pre-proposal stage. You want to reach out to either myself or Dr. Cow. We can help answer some of the questions that you might have about using the facility. Some questions you might want to ask yourself before coming to us or ask us is, what sort of equipment and instrumentation might you use? Does your testing idea fit within our capabilities, or would we need to provide new capabilities, or is it that you should be going to another testing facility? And what solicitation do you need help with writing a proposal, right? Really specifically talking about a deadline, you don't want to come to us a week before your proposal is due. We're probably not going to be able to help too much. So if you give us a lot of time, or a good amount of time, right, we can really help you get a winning proposal. And then what additional information can we provide to you that can help you with your proposal? There's some additional resources on our website. We have a guideline of sort of what questions you might want to ask for during the pre-proposal stage, and then a checklist for proposal prep. And I'll go into some more detail here. So your proposal writing stage, right? You want to have a research plan. Again, what facilities, equipment, and labor resources you'll need, a schedule, a budget, and a data management plan. We recommend that you review NSF's proposal and award policy, typically referred to as the PAPG. Specifically, Part 1, Chapter 2, the proposal prep instructions. You'll also want to review our facility users guide, which is on our website. You want to communicate with myself or Jim or Dr. Cow or Dr. Rickles, or really any of us here on the panel. You can reach out to any of us. I'm typically your main contact, but we'd all be happy to help. So again, some important information I'm going to really hammer it home is that you want to have a good research plan. You want to discuss with us what facilities and equipment you'll need, your schedule, your budget, and your data management plan. These are all typical things that you'd see in any project management, and they're really critical to success of your project. If we skip any one of these, we run the risk of being over schedule or over budget or mismanaging data, which is not what we want to do here. Again, some more detail on the research plan. Just want to have a general idea of the work envisioned and how it fits in with NHERI Lehigh, the experimental facility. You'd want a description of experimental methods and procedures required of us. And then facilities and equipment, right? What sort of resources are required in terms of equipment, instrumentation, personnel? Do we have those resources or do we need to procure them? Either equipment or instrumentation, or do we need expertise in something that we don't have? Are the capabilities required of the experimental facility established, or do they need to be developed again? Right? Do we need to go out and get some of these things? And are there additional resources that Atlas can provide that are not strictly under the NHERI umbrella? That's something that we'd know on this panel, and you can certainly ask us. And we'd be happy to provide any information. So schedule, right? A couple of big things here: physical space requirements, right? So the actual footprint in the laboratory. We often have many different tests ongoing at the same time, right? So having an understanding of how big of a test setup you need is critical. And again, equipment, instrumentation, and technical staff are all important in terms of scheduling. The budget. So again, a NSF funded project can utilize the operations and maintenance budget for some qualified costs. And then your NSF project itself will supplement with our O&M budget. Any projects not funded by NSF sources are responsible for all costs. And we have detail on our website of the responsibility of costs and a rate schedule showing how much a piece of equipment costs to utilize. You can contact me for more information on those. I can provide those documents. And then a data management plan, right? So what are the types of data that you'll need? How many samples? What software do you need to use? Do we have it? Do we need to procure it? You'll want to know the standards of using data and metadata format and content. Tommy can help here in structuring the data in a particular way, such that uploading later to the NHERI repository is seamless. And then we'll also want to know, right, what are your plans for archiving data? Do you need us to hold it and then transfer it to you? Will you be holding it? These are just the sorts of things that we want to work out ahead of time. So that's the pre-proposal phase, and then now we're on to actual execution of a project, right? The post-award stage. So first step is definitely compliance documentation and site utilization forms, right? So these are forms funneled down through NHERI through NHERI. And so what these do is make sure that everything that we talked about, I just talked about during the proposal phase, right? Scheduling, budgeting, data management plan, etc., is all spelled out, and that we as a facility agree that you have worked through that, we've worked through it together, and we come to an agreement on how we'll actually execute the project. The site utilization request form just is a form that is a formal agreement between the site, the researcher, and NHERI. So yep, I just mentioned that, right? It outlines things such as a description of the planned experiments, the experimental site, that would be us, NHERI Lehigh, scheduling, scope, all these things that we'd want to have done beforehand in the proposal portion. Right. Again, if the sooner you work with us during your proposal, the smoother this goes post award, because we'll all be on the same page and have a schedule and budget, and then a sense of what equipment you use and where and how we can use it. So research training, I mentioned that before, right? So required, certainly safety training. You absolutely need to take our safety training before stepping foot in the laboratory on a project. I know we've had some recent researchers just come in, and they've had to review our safety plan. I think some of them are on this call. Knowing how to use our equipment and controls and data acquisition are also critical. And you'll receive training from either Tommy or the other staff here. The experimental test plan is just a more detailed document with project scope and detailed list of equipment, project specific safety requirements, and anticipated project schedule. The idea here is that hopefully by here, it'll be pretty smooth. We'll have everything already outlined either through the NHERI required documents or the proposal itself. So this is really just a document that we can quickly put together. And then we can work with the Atlas Center staff in case if we need to either schedule for space, equipment, or labor. So again, we can utilize the Atlas Center staff if needed. Then we'd actually execute testing, which is everyone's favorite part here. That's the part that we're all trying to get to, actually doing the testing and the research. And then finally, a critical step here, I mentioned this before, is that the post-test data archiving, right? So all data generated during testing is required to be uploaded to the NHERI repository, Design Safe. Some of you are familiar. So Tommy, our Lehigh IT manager, will provide assistance to researchers for data management, including backup on local repository and then the NHERI repository. And then for more information on the requirements of uploading data to the NHERI repository, both requirements, how-tos, what the data format should look like, you can go to Design Safe and get some more information. I think that's all I've got. So yeah, we just wanted to thank you for everyone for coming, and we're gonna, I think, open it up for Q&A here.
Joe, one thing I wanted to add to it, this is very good.
Yeah, sure.
Some of those documents that you had presented, we have some assistance with some examples in our resources. That was, I pointed this out on the on our webpage there. It's like the facilities and data management plan. There's usually are questions that come up. So I just wanted to mention the fact that I encourage those that are preparing a proposal, and we'll direct you to that if you ask to review those documents, because we find that they're quite helpful for completing your proposal. Some of these documents sometimes are a little bit mysterious in terms of what to put in there.
Sure, yeah, and I mentioned too, right, that a number of those documents we'd certainly be putting together with you, right? So, you know, when working out a project schedule and what equipment you need, right? We will help you outline those sorts of things. So.
Our next workshop's that in-person workshop. It's around the third week of November, Joe. So we'll, I guess, post an announcement through the CI, and I assume everyone on this call, so to speak, on the Zoom probably will get an invite because they're registered before NHERI. So really encourage people to come visit us, because you got to see stuff in person to recognize the resources that we can provide you to help you do your work. And as I mentioned too, we have those pilot small group researchers workshops that we can provide some travel support for a small group to come and get hands-on, more hands-on than what you would have in the regular workshop. In addition, you can do some training and also if you have something in mind that you'd like to try to test out, a small device or something we could really put in our test beds or user test beds to acquire some data to strengthen your proposal. You're certainly welcome to do that, and NSF's endorsed that. And we have Ali Amir and Leanne Cow and Tommy and myself and Joe and Professor Richard Souse, and we all have expertise in different areas. We could provide you guidance on a number of things there. Richard Souse is a co-PI. We introduced him earlier. He didn't get a chance to speak. I don't know if he's actually wants to say hello, but he's been very instrumental. And also, he's a director of Atlas, so we have a very close working relationship with Atlas, of course, by him being the bridge between the two there. I think he's not able to join us. Well, in any event.
Tommy, do we have any questions?
There's no questions in the chat or the Q&A at this time.
There's born not raised hand, so that's what I see. Okay. If I'm
yep, I see that.
okay.
Hello, can you hear me?
Yes,
we can.
Thank you very much for the thorough presentation. It was really nice learning about your facility. Thank you all. I just had a quick question. So I'm a PhD student, and me and my advisors are thinking of submitting a proposal. So I noticed during the process of writing the proposal, you'll be able to help with some of the questions that we have. I was just curious, like, if I should hold on and then consider it to ask it officially, or is it okay, like, if I can ask it now? It's about the finite element model, I think, and stuff like that.
Yeah, I mean, you're welcome to ask anything.
Yeah.
Or maybe it helped the
sure.
audience. But if you want something that's sort of confidential because it's in your research plan, you could always contact us later. But feel free to ask us whatever you want.
Yeah, so I noticed you've been using your own analytical models. Is it okay, like, since my problem is to develop our own solver, so can we integrate what we develop, like our finite element solver, with your current workflow, especially like the data stream, things like that? So that's one question. And another question is, will there be any help with modeling the structures that you have at the facility? Like, I don't know if there are any specifications available, or if you have like a research scientist that could help with modeling the system in finite elements. So these are my two questions.
Yeah. So, Joe, do you want me to try to answer? Or...
Yeah. You can take it.
So the on the second question, yes, and yes. We can provide you a lot of help with modeling, whatever software you have. But but it depends on your application. But we have a lot of experience. For instance, Ali Amir has done experiments, and she's now doing analysis. And it is a skill, but it's something that takes a little bit of experience, and we recognize that. So we have a lot of experience and user-friendly approaches to do that. As example, if you're using OpenSeas, our own software that we run primarily because we run it in real time, and I'll get to your first question related to that. It's very similar, at least on the front page, in terms of the input to OpenSeas, and if you can recognize the syntax, it's very similar. It usually people adapt very quickly. We also have translators that we could translate your OpenSeas model to our models, but at the same time, we recognize there's a lot of modeling aspects that the only reason you model numerically is you feel confident, and you don't want to be critiqued that you have something that maybe there's an error in the model. So we could provide a lot of guidance on that. We've got a lot of experience with that, and we've all learned from our mistakes. So don't we don't want others to make the same mistake. In terms of the first question you had, it depends on the application. If you wanted to, you know, have your own model, and I guess what you're saying is, for instance, maybe using OpenSeas or SAP or something to create your model. So that's a numerical model. If you then want to use that model to run, say, hybrid simulations, Tommy's been able to interface, for instance, I'll give you an example, ANSYS. You know, we've also interfaced OpenSeas with our actuator, should I say. If you want to do it in real time, those programs really aren't conducive to do so, because they're not hard real time, and so we prefer to use a software, and we develop it for that reason, to run in true real time. So I can understand there'd be some apprehension saying, well, you understand your own model, you spend a lot of effort, but we can translate, so to speak, that into the model, that modeling capabilities we have. That we have a lot of modeling capabilities, some in fact that OpenSea say don't have, but of course OpenSea has a lot of other capabilities, so we can readily show you how to translate that model if you can't use the model you have with your existing software. It's a matter of just looking at the details, and really in the end you want to decide what's the quickest and best way to get to the goal line there, right? So we work with you on that. So I wouldn't worry about those aspects too much. I can understand you have your own software, you want to use those models, but we'll work with you on it. Does that answer your question on that?
Yeah, I think I'm a little bit clear. I think those the specific question about integrating the solver with your existing framework, I think that could be that could wait until like we go officially and talk with you guys, because I think it's a little bit more nuanced and detailed. But yes,
yeah.
Thank you very much for your explanation.
So Tommy's the integrator here. So what I would suggest there is to, and so you could maybe in the proposal planning stage just kind of discuss the bigger idea, and we can definitely foresee, you know, what it would take, and because you want to have a timeline on the work that you're going to do, and we can give you some feedback on that. You know, Tommy's done a lot of that, so he can really tell you the hard details about the nuts and bolts about all the integration there. When you say solver, Borna, I mean, that's your last name, I guess. When you say solver, I mean, I typically think of equation solver, but is that like the coordinator that you're integrating, say, equations and getting commands and getting back information and processing? I think you're calling the solver that, right?
Yes, like the actual name is Phoenix. Like if you came across that, it's an open source finite element solver.
Okay, yeah. So no, we'll work with you. I mean, we view it as an opportunity to expand our capabilities, so we don't shy away from anything there. So we'll definitely work with you on that. You know, Tommy can take a hard look at that. I suggest to do that in the planning stages, so you can then feel confident moving forward, submitting your proposal. You can work out enough details that you can feel the reviewers will be comfortable with your approach there. You have to add a little bit of credibility to what you're doing there in your reviewers' eyes.
Absolutely. Thank you very much for your thorough explanation.
Yeah, no, you're very welcome. I don't know if anyone else has anything to add there. You know, Tom, you have anything to add there?
No, nothing to add that. Yeah, I looked at them up on the Phoenix platform right now, the solver for high performance clusters and stuff. Not something that we've ever interfaced with, but it's always interesting to learn from the community what everybody's using, so that we also allow our capabilities to expand to these realms.
Yes, I think it's a good point. Yeah. Is there another question in the Q&A there that
Claudia just said, thank you for the interesting workshop. Appreciate, I mean, I look forward to seeing you all. So thank you for that.
Oh, okay. Yeah, thanks, Claudia. So I don't know, we love questions because we hope to provide good answers, but I don't know if anyone else has any questions at all. There's still about a number of people still on here. Looks like we did good timing today, Joe.
30 seconds left until it's over.
And even I encourage you to visit our webpage. The other thing also, I think is very important to mention. We're all researchers. I'm a faculty member. I submit proposals. Professor Richard Sells does the same. Leanne Cow will be positioned. He'll be able to do that as well, and Thomas Marilla. But we don't compete with who we talk to. So, for instance, if you have an idea that if I feel there's a conflict of interest, or I don't want to myself put you in a bad position, I would excuse myself from any of the technical details that you can feel that things remain in confidence. So we don't share any ideas amongst ourselves if there's a conflict of interest or with anyone else. So you could rest assured that you could discuss things to the length you want. Our mission is to provide you with a good sense of direction so you have a very strong proposal. And sometimes if you have an idea, and you may ask us, because I've personally mentored every one of those career awards, I've mentored them, except for maybe Austin Downey, but a little bit. But we can review also your proposal from a perspective of broadness and knowing the program directors. We can give you a little bit of guidance there. Your success is our success. So if you're successful in getting funded, that's meaning that you're going to use our facility. That's very important to us, because NSF really, that's what they look for, and it keeps us also engaged with the research community. So keep that in mind. I don't know, Tommy. I guess we're right at 2 o'clock.
I think we're good. I think we can thank everyone for joining us for these 2 hours. I appreciate the interactions, and then we wish everyone a good afternoon, good evening, wherever they may be. And if they ever want to contact us, I left in the chat our website. Our contact information is on there, and we will, if anyone needs any further information from these slides, that we can, upon request, provide that from the slides if they want more information. Other than that, we'll thank everybody, and then we'll end this webinar for today, unless you guys have any closing notes that you want to offer.
No,
Thanks, everyone.
I wanted to, sorry, Joe. Go ahead, Joe.
Oh, I just wanted to thank everyone. That's it.
Yeah, myself as well, and everyone on the staff for taking the time to prepare their. Richard Sells wears a lot of hats, and so he's very engaged with this, but unfortunately he didn't have the opportunity to say much. If he wants to say anything in closing, I certainly would welcome him here. I think he's taking care of another fire here. He's also the director of Atlas, so he's doing things. So anyways, thank you very much. And so we should let everyone go.
All right. Thank you all. Take care.